Okay, so starting something a little different here, getting into the gas laws, the using of gases, pressure, volume, temperature, moles, things that you guys did before. So hopefully, things like this are things you maybe remember from last year. PV equals nRT, and then PV over T equals PV over T. Um, these are gas laws. So you get the ideal gas law over here on the left and combined gas law on the right. And so you can see pressure and volume and then temperature are associated with both. And so that's where we're going to start going at this point, start getting into some of that. So first thing I want to look at is our definition says all gases have the same volume or molar volume at the same temperature and pressure. So what that means is that your identity of your gas doesn't matter. So if you have chlorine gas or hydrogen or neon, if the gas is at the same, if our gases are at the same temperature, at the same pressure, our identity is not going to matter because no matter what the gas is, we're going to use this conversion, which is that you get 22.4 liters for every 1 mole of your gas. And so it doesn't matter what your gas is because we're not using grams. Periodic table doesn't matter. So that's the thing with gases is that you have the same volume no matter what their identity is. The things that change the volume are things like temperature and pressure. Okay, so that this 22.4, we want to really remember that. That's the common one. And so in IB, you are going to see that they like to use this value here, which is the milliliter or the centimeter cubed. It's the same exact thing. It's just obviously there's more of those because they are smaller than liters. And so hopefully remember last year the centimeter cubed is the same as a milliliter. If you don't, you want to write that down. And so right here it says centimeters cubed. IB uses this one, but you could also think of it as milliliters because it's the same thing. And then 22.4 liters is the same thing. And so you'll notice that this is all happening at standard temperature and pressure. And so standard conditions, you should have learned these last year, but they're right here. A standard condition is 1 atmosphere or so units of pressure. It's also 760 millimeters of mercury. You might want to write that down. 1 ATM equals 760 millimeters of mercury. That's another unit of pressure. And so the temperature, though, is always 273 Kelvin. All right, so we're using the Kelvin, but remember that degrees Celsius are just going to be so you have your Kelvin values and your degrees Celsius values, and so degrees Celsius plus 273 is going to equal your Kelvin value, and so that's going to be the same as 0 degrees Celsius. So 273 Kelvin would be the same as 0 degrees Celsius. So just some things maybe that might help you out here. Don't quite need them right yet. But I do want to point out this last piece here. 1 liter is the same as 1 dm cubed. So that's a decimeter cubed. IB being an international curriculum, this is much more of a European unit. They use that much more than they would a liter. They are the same thing. And so I want you, when you see that DM3, I want you to think liter, right? So DM3, you're thinking liter. And then DM minus 3 is actually liters on the bottom, like 1 over liters. So when you see that negative exponent, that just means it's going to be on the bottom. All right. So let's go down here to and we talked about standard temperature and pressure. So go down here to our example, and it says what volume of hydrogen forms when we have 300 centimeters cubed. Remember, right away you're thinking, oh, centimeter cubed, same as a milliliter of nitrogen is formed by the complete decomposition of ammonia. And then there we are at standard temperature and pressure. So in your, since you're all excellent, fantastic chemistry students, you should see STP, and in your brain, you should right away be thinking, oh, I'm probably going to be using 22.4 here somewhere, because STP is normally given as a hint or a gentle nudge that's like, hey, you awesome chemistry student, you are getting a big fat clue, and the big fat clue is the STP, which is supposed to lead you to the 22.4. So anyway, what we don't have here is a formula, and this definitely is a stoichiometry problem. I know that because I have one chemical and they're talking about a different one. So I'm going from one to another, and so that is definitely going to be a stoichiometry problem. So let's go ahead and run the equation through here real quick. I guess this is a good time to point out that knowing what ammonia is pretty useful, and ammonia is NH3. So they said that it decomposed. So hopefully you remember from last year how that works. So decomposition would be, get a little space here, it would be NH3. Decomposition means it's going to break down, and so it's going to break down into those two items, hydrogen and the nitrogen, and then those guys are diatomic because they are in Brinkelhoff. So now we're going to go and balance it up real quick. So the nitrogen's going to put a 2 here, which gives you 6 H's, so we'll put a 3 there, and so that is what we have. Okay, let's put the important bits on top, and so give us a little bit of space here. It says we have what volume, so what volume of hydrogen means I'm going to put a question mark above hydrogen, and when you see the word volume, that's going to mean liters. And so you might want to make a little note to yourself that okay, volume is what led me to knowing that they want to answer in liters. All right, so they give us this number, and it's nitrogen, so 300 centimeters cubed of nitrogen, and you could also think of that as a milliliter, and that might help you out. All right, so going to put a big fat X over this, and so you're basically going to go from one chemical to another, so that requires stoichiometry. That's going to require a mole ratio, and so in order to do that, as in most chemistry problems, we have to actually get to moles. So our goal will be to take the volume, the only number they give us, so we're going to write that down. So 300 centimeters cubed of the nitrogen, and we need to turn it into moles. Okay, so the best way to do this is to recognize that we can use the 22.4, and so we want to use this conversion factor, which is 1 mole is the same as 22.4 liters. So we want to use that. That's the STP conversion factor. So the problem you have is that these are not, those are not liters. Those are milliliters. And so you might want to jot down to yourself that those are the same as milliliters. Oh, don't want to do that. Want the pen. Here we go. Okay, so they're the same as milliliters. So how can we cancel them out? Well, good chemistry student thinks to themselves, okay, I know these conversions. I don't want these centimeters cubed or milliliters, so I'm going to put them on bottom. And so I'll put those on bottom. It's the same thing. And then on top, I'm going to put liters. So which unit is bigger, the liters or the milliliters? Well, the liters are bigger. They're quite a bit bigger, so they get the 1. And then does milli mean 100 or 1,000? Well, milli means 1,000. And so that's kind of how I would do it. And so then you have these canceling out, and now you have liters. Now that you have liters, you can convert your liters into moles. And you do that by putting 1 mole on top and 22.4 liters on the bottom. And so we are using this right here as our conversion factor. It's not hard. You don't have to add anything up, but it is something that you do want to recognize how to get that. All right. So now that we're in moles, we're able to go from chemical A to chemical B. So once you're in moles, you can do that back and forth thing, and we call that the mole ratio. So let's go ahead and do that mole ratio. So remember, the chemical that we want is going to go on top because we're going to create that one, and the chemical we have already goes on the bottom. And then we use the values in front, those coefficients, and they're going to become our numbers in our problem. Okay, so stuff that we've done before. So it looks like the hydrogen's on top, so we're going to go 3 moles of that one. And then on the bottom, that's a 2, not a Z. A lot of times my 2s look like Z's, so you gotta kind of watch me. So here we go. And then on the bottom, 1 mole of the nitrogen. Okay, boom, there we go. And we could stop right now if they wanted moles, but they don't. They sadly want liters, but that's fine, because for every 1 mole, it doesn't matter what chemical you have, you get 22.4 liters. All right, so then we can go ahead and check our units real quick. The liters is on top and bottom. The moles are on top and bottom. The nitrogen's on top and bottom. And there's another mole. And so here we go. We've got hydrogen in liters. And that's exactly what we were looking for here. Liters of hydrogen. So that's good stuff. So let's run it through our calculator. And so I know that some of the math cancels, but the units are kind of why we put it in this order to make sure we could see the units. So 300 divided by 1,000, hit enter. Divided by 22.4, you hit enter. Multiply by 3, hit enter. And then dividing by 1 doesn't do anything, so times 22.4. And then we got an answer of 0. Oh, don't want that. 0.9 liters of our hydrogen. So that would be your answer. And so I know that you